And the first thing I want you to write beside this is that this a is outside the function, and it affects the y-coordinate. So what we're going to do is we're going to look at these different points that they have, and we're going to look at the original function. And the original function, we have this point 16, 4. That makes sense because the square root of 16 is 4. When we look at what happens on the green graph, and one of the things that we're going to do when we look at each of these, I'll start from the top. We'll start from the blue graph. So if I look at the blue graph, on my original graph, I have 16, 4. What we're going to do sort of as notation is we're going to show how particular points are going to change. So 16, 4 is a point on my original graph. But on my blue graph, I have y equals 3 times square root of x. What that's going to do is that's going to multiply my y values by 3. So it's something outside of the function affects the y values, and it's going to affect them exactly by what you see. If you're multiplying by 3, you're going to take your y values and multiply them by 3. So we would get the point 16, 12, and you can see that that is what matched up with our graph. If we looked at our green graph. So again, starting with my original point on my red graph, on my green graph, I have a 2 out in front. So I'm going to multiply my y values by 2. And just sort of as, notice the first time I wrote multiply just so you have it in your notes. After that, you'll probably just say y by 2. That is simple. It explains what you're doing. And then where does that point go? My y-coordinate is getting affected. It's going to 16, 8. I'll only do one more. Maybe I'll do the purple one here. 16, 4. If I go here, now I have a 1/4 out in front. Even if it's a fraction, you multiply that. So I'd multiply all my y values by 1/4. And that's 16, 4. If I multiply 4 by 1/4, I get 16, 1. So we could do the orange one as well. You're going to multiply by 1/2. This transformation we call a vertical stretch because our original graph is getting pulled away, stretched away from the x-axis in the green and the blue one, and we would say it's getting compressed towards the x-axis with the orange and the purple one. So these transformations would be called vertical stretches and vertical compressions. Anytime you're multiplying your y values by a number bigger than 1, you'll call it a vertical stretch. Anytime you're multiplying by something less than 1, you're going to call it a vertical compression. So if we look at the second example, now these ones are of the form, is that how they've written it? They put a B? Yes. This one is inside the function. We'll write that down. And since it's inside the function, it affects the x-coordinate. So notice on our original graph, again, our original graph here is in red. They start with the point 4, 2. And they say, what happens to 4, 2 when we have these different things in our equation? So again, I'm going to start with the blue one. I have the point 4, 2. And in our blue graph, which has the square root of 4x, again, you see the 4, and you'll probably say, or probably be tempted to say, let's multiply our x value by 4. because that's what we did with our y values. But just like translations, you remember with translations when there was a +3, you went 3 to the left, and when there was a -2, you went 2 to the right, and you sort of went opposite. The same thing happens with stretches and compressions. If there's a 4 in there, we're going to multiply by the reciprocal, which is the same as dividing, but we're going to use the word multiply because especially when we're dealing with fractions, that's going to be easier. So we're always going to multiply by the reciprocal. So if I started with 4, 2 and I multiply my x by 1/4, I get 1, 2, and that matches up with this point right there. Now in this case, it looks like, if I look at the red to the blue graph, you might say, hey, it looks like it's been stretched vertically, right? And sometimes that happens. Stretching vertically is the same as getting something compressed horizontally. So the way this equation is written right now in blue, I would say that's a horizontal compression by a factor of 1/4, because that's what we've done. We've multiplied our x values by 1/4. If we look at the green one, so we start with 4, 2 on the green graph. There we have a 2 inside of the function, so you would multiply your x values by 1/2, and you would end up with 2, 2, and you can see that that matches up with that point on our green graph. Again, we'll just do one more. We'll do the purple one. So what happens to 4, 2 on the purple one? Now there is a 1/4 inside of our function. We would multiply by the reciprocal. So the reciprocal says we take that fraction and flip it, so it becomes 4/1. So you're going to multiply your x values by 4, and your new point over here is going to be 16, 2. So each of these, when something is inside the function, is either going to be a horizontal stretch or a horizontal compression, depending if that number, right, if that number is bigger than 1, when you do the reciprocal, you're going to multiply by something less than 1, and those ones will be horizontal compressions. And when the number inside is less than 1, then you're going to multiply by the reciprocal, and that will be a horizontal stretch. Just for fun, you could simplify the blue one. What's another way that I could write that blue equation? You could, because the square root of 4 is 2, so you could have written this as 2 root x. If I wrote it that way, I would no longer be talking about horizontal stuff. Now that 2 is outside, and I'd be talking about a vertical stretch. So I said before, sometimes horizontal compressions look like vertical stretches. In this case, that's true, because what would happen if I did a vertical stretch on the point 4, 2 with the 2 out in front? I would get the point 4, 4, and that matches up on the graph as well. So depending on how you look at the equation, it could be more than one way of seeing it. In this case with square roots, stretching vertically by a factor of 2 is the same as compressing horizontally by a factor of 1/4. So what you're going to be asked to do is graph these. They're going to give you the equation, and you're going to have to graph them. Now, if you were graphing y equals the square root of 4x, and you thought of it as horizontal compressions, and did that all the way along, you would get the same graph that you would if you took it and stretched everything. And our last one to look at here is with both combined. So we've got both of these, so we will have horizontal and vertical stretches slash compressions. And when we're showing our work, so the point that they've given us on our original graph, again, is 4, 2. There's our parent graph. That's the graph that you have got memorized. You'd probably know these 3 points really quick, 0, 0, 1, 1, and 4, 2. And when you're showing your work, what you're going to do is you're going to say, I'm going to take my point 4, 2, and start with my blue one. If I was looking at that blue graph, I see that I have a 4 outside of my function. That's going to affect my y values. And I'll make a little note here that I'm going to take my y values and multiply them by 4, because that's what that 4 outside is going to do. And inside, I see a 2. That's going to affect my x values. So I'm going to write under the same arrow that my x values are going to get multiplied, and everything horizontal is the reciprocal. So my x values are going to get multiplied by 1/2. So if I did that, my x values multiplied by 1/2, my y values multiplied by 4, I get the point 2, 8. So in graphing the blue graph, you would probably do this to all 3 of your key points. And we'll just do the blue one here. So if I took 0, 0 and did the same thing, I multiplied y by 4 and x by 1/2. Well, this is really easy mental math because they were both zeros, and you multiply them by something. It's still going to be 0, 0. If I take 1, 1, I multiply my y by 4 and my x by 1/2. Well, my x will be 1/2, and 1 times 4 is 4. So we notice on this graph that we would be able to draw these 3 points from our original 3 points of our parent graph. And then once we have those 3 points, we would connect them, not with straight lines, because we still need, if the original graph has a curve, even after stretching and compressing it, it will still have that same curve. It will just be, in this case, a much steeper curve than the one that was original. So now we can see these things happen with whatever parent graphs that we've had to start. So on the next page, they've got an example here with an x cubed graph. There's our x cubed graph. Now, if you had a 1/2 out in front of that x cubed graph, that would be a vertical compression by 1/2. And this is our first example where we have something above the x-axis and below the x-axis. So when we're doing a vertical compression or a vertical stretch, it's compressed towards the x-axis. So can you see that if I took that red graph and from the top and the bottom I kind of squished it, it would turn into that green graph? And stretches are like pulling away, up and down, away from the x-axis. Here, if you had a 2 in front of the x cubed, that would take that red graph and you would pull away from the x-axis to stretch it. Can you see how that red graph could get stretched to become that orange graph? And what's happening algebraically is you're taking your point. So in this case, they're starting with 2, 8. And in orange, ooh, do I have an orange pen? Yes, I do. I get 2, and I'm multiplying my y values by 2. It becomes 2, 16. And that's what causes it to stretch. All right, so let's look at another one with x cubed. This time we're going to look at, did we do this one already? No, this time they put negatives involved. So the negative involved will still stretch it and reflect it simultaneously. And we're going to do that. So here I've got the point 2, 8 with a negative 2 out in front. I'd multiply my y values by negative 2. And if you do those both at the same time, can you see that the green graph is getting stretched and reflected over the x-axis? But we can do that all in one step, because the only thing we need to do is multiply our y-coordinate by negative 2. So here they summarize that, and the way that they're trying to summarize that for your vertical stretches is that they have right here is the value of a in front, and they're showing you that in the point you're going to multiply your y-coordinate by a. So all of these extra words you don't worry about it, because this is when it's abstract with like what they're doing is they're saying a could be any number, but I think that we're able to see it with the examples that we've done, what makes something stretch vertically, what makes something compress horizontally, compress vertically as well. Okay, so let's do example number 1. Here we have the graph of y equals f of x. So it's in function notation, something to note at the beginning. Sketch the graph of y equals negative 1/4 f of x. State the domain and range of each function. So I look at my original function f of x. I look and I say, here's a key point, 0, 0, because that's sort of the vertex. That's going to be an important one. I'm going to look at some other points as well. I'm also going to look at what I'm going to graph. Can you see that we have here a vertical compression? And are you okay with these abbreviations? A vertical reflection? What it means algebraically is we are going to multiply our y values by negative 1/4. We can combine both the vertical compression and the vertical reflection together with one thing algebraically. Multiply by negative 1/4. So if I took the point 0, 0 from my original graph, and above this arrow I'm going to say what I'm going to do. I'm going to multiply by negative 1/4. Well, that one's really easy mental math. That's going to stay 0, 0. Now I need to choose some other points, because just having one point on my new graph doesn't really let me connect the dots very well. So I'm going to need some more points. I'm also going to pre-plan which points I'm going to choose. Because there's, especially on this one, there's lots of points I could choose. But I'm going to do some thinking, and I'm going to say, well, I know that I'm going to multiply my y-coordinates by 1/4. I could choose 1, or 2, 2 here. But then I'm going to get a fraction. And then fractions aren't bad. I quite like fractions in a lot of situations. But if you can avoid fractions, usually it's nicer. So what would be a nice point to choose on my red graph? Four, 4. Because if I choose 4, 4, when I multiply y by negative 1/4, it turns out to be a fairly nice number, 0, negative 1. Sometimes we've got to be careful on these scales, because I can see some of you doing exactly what I'm going to do right now. And tell me why this is wrong. Okay. Whoa. I also made what should this not be 0, right? This should be, the x didn't change. It should stay 4. So I'm going to label the point 4, negative 1. And I'm going to make the same error that if you were working ahead, some of you might have made this error. What did I do wrong? 4, negative 1. There we go. What's wrong with that? That point's at 2. The scale on this one is going by 2s, right? But so often we're used to grids going by 1 that you'll probably just count, 4, negative 1. Okay, this one would actually be, there we go, right there, right? If you wanted to do another point, you could do This one would be a nice point, or 1 on this side would be a nice point. If I took negative 8 comma 8, where's it going to go? The x value doesn't change, but dividing by negative 1/4, it's going to become negative 8 and negative 2. This one would go right there. Now that we've got these 3 points, there's our new graph. Can you see that our new graph has a vertical reflection? It's been flipped down, and it's been compressed. It's been squished towards the x-axis. Now, this was in function notation, but maybe you recognize the red graph. If I asked you for an explicit equation for the red graph, an explicit equation doesn't have f for functions in it, it just has y's and x. What's another way you could have written this equation? You recognize it as the absolute value of x? So if I had asked you for an explicit equation for the blue one, can you see that an explicit equation for the blue one could have been, well, if we look at this, what's happened? We've got a negative 1/4 in front of f of x, so we would have a negative 1/4 in front of the absolute value of x. So you could have been asked this same question given these equations, the explicit equations, or in this case they gave it to us in function notation. So we do want to be able to go back and forth between two different notations and understand how both of them work. Question for practice on this one is number 3.